Hello, in this video, we're going to go over the completeness axiom. As we discussed in the previous videos, there are some certain properties of real numbers that are also apply for other types of numbers. For example, the field axioms is a property that applies to many different kinds of fields: field of rationals, field of real numbers, and field of complex numbers all satisfy these properties. And then another property, which is the positivity axiom, which also applies to the real numbers and rationals and other types of ordered fields. However, the completeness axiom is the one that distinguishes rationals from real numbers. And what it basically says is that there is no hole in real numbers. Now, what does that mean? Let me talk about that idea, and then we'll talk about the rigorous statement of the completeness axiom. So what it means is that if you think about the set of rationals that are below square root of 2, so 1 is a number below square root of 2, and 1.1 is also below square root of 2, and so on. You see that these numbers that are below square root of 2, they are going to approach square root of 2, but square root of 2 is not inside rational numbers. It's an irrational number. So what does that mean? Well, how do we in fact think, how can we in fact think about that? The way we can think about that is that there's a hole inside rational numbers, which if we fill all of those holes, we get the set of real numbers. Now, the way we can say that is that if you have a set of real numbers that is bounded above, which means it doesn't go to infinity, there is a number that is right above the smallest number that is above the set. In other words, it brings us to these definitions. The first definition is a set of what is a bounded set. A set S is called bounded above if there is a real number R for which S is less than or equal to R for all S in S, which means you have a set that doesn't go to infinity. This number R is called an upper bound for S, and the least upper bound, which means the smallest upper bound of S, is called the supremum of S. Now, this number in the definition, we don't know if it exists or not. If it exists, we call it the supremum of S. Similarly, S is called bounded below. So if you have a set S, it is called bounded below if there is a real number R, which is less than or equal to everything in S. The number R is called a lower bound, and the greatest lower bound, if it exists, is called the infimum of S. Supremum of S is denoted by SUPS, and INFS is the infimum of S. That's called infimum of S. Now, the completeness axiom tells us that in fact these two numbers, in fact it tells us that supremum exists, and then we are going to prove that the infimum also exists in a theorem. Okay, so let's start with an example. So we want to find the infimum and supremum of the set 0, 1. And as I mentioned, if a set is both bounded above and bounded below, we call it a bounded set. So let's start with this example, a simple example in what is the supremum and infimum of this set. If you think about this set intuitively, if you think about set from 0 to 1, intuitively, everything above 1 is an upper bound. And the smallest of them is in fact the number 1. So in order to show 1 is an upper bound, in order to show 1 is the supremum, we have to show two things. First, 1 is an upper bound, and second, nothing less than 1 is an upper bound. Okay, so first note that if X is inside this set, then X is less than or equal to 1. Thus, 1 is an upper bound. For the set 0, 1. Now we have to show that this is in fact the smallest upper bound, which means Anything less than that is not an upper bound. So we will show 1 is the smallest upper bound for the set 0, 1. Let's assume x is less than 1. So I'm going to basically use proof by contradiction. So assume on the contrary, x less than 1 is an upper bound for the set 0, 1. So what happens if, in fact, this is an upper bound? What we're going to show is that that's not possible. And the reason is this: if you intuitively think about that, let's say there's an x here that is an upper bound. Well, you can find something in between x and 1 that is inside the set 0, 1, which is why that is a contradiction. So how do we articulate that? We have to take something between x and 1. And the most natural number would be the average, if you take x plus 1 over 2. However, if your x is far below 0, which of course it shouldn't be because it's an upper bound, then your average could be, if your x is, say, here, if your x is here, then the average would not be in the set, 0, 1. So we'll have to take that into account. So here is now how I would write on the rest of the solution. So since x is an upper bound, x is greater than or equal to, let's say, 1/2, because 1/2 is in the set. Now let's look at the number 1 plus x over 2. This is certainly less than 1 plus 1 over 2, which is 1, and is greater than, so I'm going to, in fact, substitute x by 1/2 over 2, which is clearly positive. So that means 1 plus x over 2 is in the set 0, 1. However, as we saw in that diagram, 1 plus x over 2 is greater than x plus x over 2, which is x. And this is a contradiction. So we just showed that 1 plus x over 2 is in the set 0, 1, but it is more than x. So that means x cannot be an upper bound. So that's a contradiction. So in order to show 1 is the supremum, I showed 1 is an upper bound and nothing less than that is an upper bound. And then similarly, so the other part would be similar. Similarly, 0 is the infimum. So let me finish this up. Therefore, supremum of the set 0, 1 is equal to 1. Similarly, infimum of this set is 0. Okay, so that's the end of this, this example. Now we're going to talk about the completeness axiom. So completeness axiom states that every set that you take, as long as it is a non-empty set, so you have to check these two conditions. It is a non-empty set and it is bounded above. It has a least upper bound. Supremum of that set exists. So if you have a set that is non-empty and bounded above, these two conditions must be checked. Then S has an upper bound, has a least upper bound. Okay, so given that, we are going to show the existence of infimum. So we showed that this completeness axiom, this axiom tells us every set that is bounded above and non-empty has a supremum. Now we're going to show that every set that is bounded below and non-empty has an infimum. So we have to relate these two facts. So something that has an upper bound and non-empty. to something that has a lower bound and non-empty. So, okay, so if something has a lower bound and non-empty, we can turn it into a set that has an upper bound and non-empty. So let me write down the proof of this one. So we have to think about how we can turn a set that has a lower bound to a set that has an upper bound. The way you can do that is by some sort of a reflection. So if this is your set, let's say S, that has a lower bound, you can reflect it about 0. So if this is 0, you can reflect it about 0, and you get a set that has an upper bound. So let's start with the proof. So suppose S is a non-empty subset of real numbers that is bounded below. Okay, so we're going to turn that into a subset of real numbers that is bounded above. Let T be the set of all negative S such that S is in S. Okay, so we will apply the completeness axiom to T. So we will have to show T is non-empty. So that's clear. Since S is non-empty, T is non-empty. Then we will have to show that T has an upper bound. Since S is bounded below, there is some real number, let's call it R, such that R is less than or equal to S for all S in S. So that means negative R is greater than or equal to negative S. And that means negative R is an upper bound for every element of T is of the form negative S, is an upper bound for T. So now that T is non-empty and has an upper bound, we can apply the completeness axiom. Therefore, by the completeness axiom, T has a least upper bound. So we have a least upper bound for T. So let's call that, let supremum of T be some element T. We will show that, in fact, infimum of S is negative T. So going back to the diagram, if this is this would be our T, and if this is the supremum of T, then this would be infimum of S. So this would be negative supremum of T. So we're going to prove that. And how do we prove that? So this is what we're going to do. So claim is infimum of S is equal to negative T. Okay, so first again, when we want to show something is infimum, we need to show two things. First, it is a lower bound, and second, nothing more than that is a lower bound. So note that if S is in S, then negative S is in T, which means negative S is less than or equal to T, which means S is greater than or equal to negative T. So that means negative T is a lower bound for S. So we showed that negative T is in fact a lower bound for S. The next thing we need to do is to show that nothing more than negative T is a lower bound for S. So suppose X is more than negative T. We will have to show X is not a lower bound for S. So this means negative X is less than T. Since supremum of t is t. So supremum of t is t, which means negative x is not an upper bound for t, because negative x is something less than the supremum. So negative x cannot be an upper bound. Thus, there is some y in t such that y is greater than negative x. But since y is in t, every element of t is minus some element of s. Let's call it S1. So we have y is negative S1 for some element of s. And that means negative S1 is greater than negative x, which means S1 is less than x, which means x is not a lower bound for s. So what we showed is that negative t is a lower bound, and nothing more than negative t is a lower bound. And therefore, negative t is the infimum of s. So this completes the proof. We showed that the set S has a largest lower bound or infimum. So this finishes the proof for the theorem. Okay. So the last thing we're going to do today is one more example. This one is a more complicated example on Supremum. Okay, so one other remark. This is kind of an intuitive one. If your set is not bounded above, then we say its supremum is infinity. So if it just goes to infinity, if the terms of this, if there are elements in the set that go to infinity, we say the supremum of the set is infinity. And if it is not bounded below, then we say the infimum is negative infinity for non-empty sets. Okay. So let's look at the next example. So suppose C is a positive real number. Prove that there is a unique positive real number X for which X squared is equal to C. So what I want to do here is I want to show that every positive real number has a square root. So this is something I haven't really proved. So I haven't proved that there is a square root of 2. There is a real number X that when you square it, you get 2. So we haven't actually proved that. And this is something I'm going to prove. So if you take a positive real number C, there is a positive real number X that X squared is equal to C. What we're going to do is we're going to define this X as a supremum of a set. So define a set S to be set of all S such that S squared is less than or equal to C. Then we're going to show that this set S has a supremum, and then we're going to show that the supremum is in fact a satisfies X squared equals C. Okay, so the claim is S is non-empty and bounded above. The reason we need this is we would like to apply the completeness axiom because we would like to show it has a supremum. In order to show it has a supremum, we will have to show it's non-empty and it is bounded above. Non-empty isn't that difficult because 0 squared is 0, which is less than C. And that means 0 is in S. So that tells us that S is not empty. Now, we will have to show it is bounded above. I cannot really take the square root of both sides. I cannot say S squared is less than C, therefore S is less than root C, because I don't actually know root C exists. But what I want to show is that the elements of the set do not go to infinity. So if S is very large, S squared cannot be less than C. So if S is, let's just do kind of the scratch work here on this side. So I want to show if S is large, some like A, then S squared is going to be more than C. If I show that, then that means S is not in the set. What I'm trying to find out is what is A. So let's do that. If I square both sides, I get A squared. I would like A squared to be more than C. So I'm looking for something that when I square it, it's more than C. Well, C squared more than C isn't always true. This is only true if C is more than 1. So maybe I can make it larger. Maybe I can make it as A equals something larger than C, but also larger than 1. So maybe C plus 1. And if you do that, then you would see that that would work. So if S is more than C plus 1, then S squared is more than C squared plus 1 plus 2C, which is more than C. And that would mean S is not in the set S. So that means C plus 1 is an upper bound for the set. Because everything more than C plus 1 does not belong to the set, which means everything in the set is less than or equal to C plus 1. So what we showed is that the set S is non-empty and it is bounded above. And when we find out that it is non-empty and bounded above, we know that it would have a supremum. So by the completeness axiom, X equals supremum of S exists. Okay. So now that we have shown this supremum exists, we would have to show that it satisfies these things. It's positive, it satisfies X squared equals C, and it is unique. There aren't multiple X values. So first, we're going to show that X is positive. Okay, so this, we know that it already exists. So note that X is positive. Since, well, we would have to show there is something, we would have to show there is something in the set that is positive. So if we can show there is some element in the set that is positive, then it would be a positive real number. Since S contains some positive real number. Now, we'll have to see why this is true. Okay, so you can think about why this is true. Why can I find something in the set that is positive, X squared is positive, and X squared is less than or equal to C. So this is what we are looking for. So you can think about some element in between that is positive. So maybe you can think about, like, say the number 1. 1 doesn't necessarily work, so it depends on whether C is more than 1 or C is less than 1. Maybe you can think about C. Does C work? C squared less than or equal to C. That works only if C is less than or equal to 1. So basically, there's two possibilities. If C is more than 1, then 1 is in the set. If C is at least 1, then 1 is in the set. And if C is less than 1, then C is in the set, since C squared is less than C. So in any case, there is something positive in the set, which means supremum is always positive. So that's the first condition, that it's a positive real number in the set. The next thing we need to show is that it satisfies x squared equals c, and that's the difficult part. And finally, we'll have to show it is unique. Okay, so now we will show x squared equals c. And the proof of this one would be by contradiction. So we're going to assume it is not equal to c, and we're going to get a contradiction. So on the contrary, assume x squared isn't c. There are two cases. So by the positivity axiom, either x squared is less than c or x squared is more than c. So we're going to look at the first case, x squared less than c. And the other one, I will let you deal with that because they're not actually that different. Although they are different, but the ideas are similar. So you cannot just write down one of them. You will have to write down both of them. So if x squared is less than c, then, so let's see what we have. What we have is c is here. Every element of the set that you take, s squared is less than c, and x squared is somewhere around here. X squared is less than c. So what I need is I need to find some element like s squared between these two. If I do that, if I do some maybe like t here, which would be x plus something, that if you square that, it remains less than c, then we are done. So what we're going to do is we're going to find something larger than x whose square is less than c. So let me write it down. We will find some positive epsilon such that x plus epsilon squared is less than c. And this is kind of explains why I'm doing that. Okay, let's simplify this expression and see what we get. So we're going to do the scratch work here, and then we're going to write down the proof here. So we get x squared plus epsilon squared plus 2x epsilon less than c. Okay, so there is an issue with epsilon. If I want to find epsilon, so I have to solve for epsilon. This is a quadratic, so it's a little bit difficult to solve because we don't have we cannot deal with square root. That's the main reason we are doing this example. So I will have to turn this into some linear expression. In order to turn this into a linear expression, we're going to turn epsilon into epsilon squared into epsilon. However, in order to do that, we need epsilon to be less than 1. So this gives us x squared plus epsilon squared plus 2x epsilon less than x squared plus epsilon plus 2x epsilon. And then we're going to make this one less than c. And in order to solve this, this is now a linear inequality. That's easy to solve. So this gives us epsilon less than c minus x squared over 1 plus 2. I'm sorry, this has got to be x epsilon, 2x. So now notice that we need these two things. We need s epsilon less than 1, and we need epsilon less than c minus x squared over 1 plus 2x. We need these two things. So we're looking for some positive epsilon, and of course, epsilon is positive to begin with. We need some positive epsilon that satisfies these three things. So the way to handle this would be to take minimum of 1 and c minus x squared over 1 plus 2x, but you wanted to make it even smaller. So you could just halve that. So here's now what we're going to do. Let epsilon be minimum of 1/2 and c minus x squared over 2 times 1 plus 2x. So note that epsilon is less than 1 and epsilon is positive. Let me put it here. Epsilon is between 0 and 1 and epsilon is less than c minus x squared over 1 plus 2x. Epsilon is positive because c is more than x squared because of that. So we get this from here. Now, if you take x plus epsilon squared, now we're going to have to repeat what we wrote to the right to just put it in the correct format. This is x squared plus epsilon squared plus 2x epsilon. That's less than x squared plus epsilon plus 2x epsilon, which is x squared plus 1 plus 2x epsilon, which is less than x squared plus c minus x squared, which is c. So this means x plus epsilon squared is less than c. So now, going back and thinking about what the set S was, the set S was all of the elements that when you square them, you get less than c. So that tells us x plus epsilon belongs to the set S. But this is a contradiction, and think about why this is a contradiction. And this is since x plus epsilon is more than x, and x was the supremum of S. So that is a contradiction. So what we just showed is that supremum squared cannot be less than c. The second case you'll have to take a look is what happens if x squared is more than c. And that's a separate issue. So if I'm not going to write down the solution to that one completely, but it's a similar process. But it's not really identical. So this is something you do have to write. So if we will find some epsilon positive such that you'll have to make this a little bit smaller. X minus epsilon squared, x minus epsilon squared is more than c, and x minus epsilon is positive. So this is all. I will leave that to you to work that out. So this needs to be worked out. It's a similar process, just square that and solve for epsilon. It's a little bit even easier. And the next thing we're going to do is, the final thing we're going to do is to show the uniqueness. So here's the uniqueness. So suppose x squared is equal to c and y squared is equal to c, and x and y are both positive. So this gives us x squared equals y squared, which means x minus y times x plus y is 0. And that implies x minus y is 0 because x plus y is positive, which means x is equal to y. So in order to prove uniqueness of some object in mathematics, we assume there are two, and then we're going to show that those two are in fact identical. And that's exactly what we did. So we assumed there are two, x and y satisfying the property that they gave us. And then we showed that that is in fact, the two must be the same. Finally, we are going to state the definition of the square root. So note that by the zero product property, x squared equals 0, if and only if x is equal to 0. This, along with the previous example, brings us the following definition. So let me kind of relate the note that I have here with what we did here. So here in this example, we showed that there is a number x satisfying x squared equals c. and it's unique and it's positive. But here C was a positive real number. Now, if you have C 0, then there is a unique number that when you score it, you get 0. And that's just 0. 0 scored is 0 and nothing else scored is 0 because of the zero product property, which follows from the properties of field axioms. So if you put these together, we can state this definition. Let C be a non-negative number. So instead of positive, I changed that to non-negative because it could be positive or 0. The square root of C denoted by root C is the unique non-negative real number x satisfying x squared equals C. So in this video, in the last portion of the video, we showed the existence of square root. And this video was all about the completeness axiom. So I will see you in the next video. And if you would like to continue watching these videos, feel free to subscribe. So next time, we're going to continue with the concept of the completeness axiom, and we will see some of the applications of that. I will see you in the next video.